Okay, in this video, we're going to keep using some of our more advanced math tools to do physics. So at the end of the last example, I did a limit, right? I said, what would happen if that point where we were evaluating the electric field got really far from the rod, and we found out that the rod started looking like a point charge. Now we're going to use what's called the binomial expansion, or really what it is a part of doing a Taylor expansion, which is related to the Taylor expansion or the Taylor series. Okay, to get an actual approximate equation. So let's go ahead and remind us what we're doing. We've got our rod, it's got a length L, and we're evaluating the electric field some distance away from it at a point P, and that distance is given by a value X. Together we figured out that the electric field at that point X in the X direction is equal to 1 over 4 pi epsilon naught, and then L divided by X times X squared plus L squared to the 1/2. Okay, I'm going to write that in a slightly different way. I'm going to take all this stuff and I'm going to put it in the front. I'm going to pull an X out of a factor in X out of what I got in the parentheses here, and I'll tell you why we're doing that in a second. Basically, I want to be able to make a really meaningful approximation here. And again, if I take, say, X to a really big number in this part of the equation, that's just going to take this whole term to a big number here. If I take X to a big number, this part of the equation is going to go to 1. That's one way to think about why we factor it out. Okay, but let's recall what the binomial expansion is, what it tells us generally. Okay, so generally if I've got 1 plus, we'll use this epsilon here, a squigglier one, 1 plus epsilon to the n, okay, the binomial expansion tells me that is going to be equal to this series here. So n times epsilon, 1 plus n times epsilon plus n over n minus 1 over 2 factorial times epsilon squared. And I can continue writing terms that are going to be similar, right? Each one of these terms is getting smaller like epsilon to some power. So this term is already smaller like epsilon to the second power. So as long as this epsilon is small, for small epsilon, it is sufficient to take the first few terms. And that's because these other terms that are multiplied by epsilon to some larger powers will get very small. Okay, so let's apply this approximation to our equation for the electric field. If I take just this part, the binomial approximation, it's a little bit easier actually. Let me write this like this. 1 plus L squared over X squared. The binomial approximation tells me to first order, this is going to be approximately equal to 1/2 times L squared over X squared. Okay, so this approximation means that now I have an equation that tells me not just what the electric field trends to, but I've got a higher order term, basically. I've got a term that tells me the first order of the error, how big the deviation from our previous approximation it is. So if I look at this and I rewrite it, this is more useful because this part's basically telling me what we already figured out. This part looks like a point charge, but now by using the binomial expansion, I have a higher order term here that tells me, right, to first order how much it deviates from a point charge. This here is small, okay? That's going to be small if x is much, much greater than L. But what it does tell me is that there is a bit, the field is a wee bit smaller, just a little bit smaller than a point charge, which makes sense because if I have this point, even if I put this point really, really far away from the bar, there's still some size here that's going to cause some field to be to the left or the up and down direction here. And those little bits of vector that are up and down are going to reduce the magnitude of the electric field relative to whether or not it was a point charge. Okay, so this gives me a higher order approximation than what I did before. And this is why being able to apply something like the binomial expansion to an equation like this is really useful.